My talk today is on the characterization of crack tip fields, and the tack I'm going to take in this talk is to consider the advances we have made in our full field capability of measuring crack tip fields experimentally and in our numerical analytical techniques, but the lack of progress in my view in terms of physical understanding of some key aspects of fatigue crack tip fields, namely crack tip shielding. I want to explore the linkage between the techniques that we've had over the past 30-40 years to characterize crack tip fields and how that's impacted on the development of our understanding of the underlying physical phenomena. And what I hope to illustrate, as I've already said, is that our experimental capabilities expanded very dramatically, but our physical understanding of the influential factors on crack tip fields and fatigue mechanisms has largely stalled in key areas, and these include the crack tip shielding I already mentioned, mean stress influences, and overloads. So I'm going to make observations on why the linkage has not been effective between our understanding of physical mechanisms and our experimental and numerical capability, as it might have been. And I believe that some of the reasons for this are conflicting rationales for undertaking fatigue crack research, which I shall expand on, variability and conflict between data from different workers on similar alloys and under similar conditions, probably the role of residual stress or strain fields versus the applied fields, the probabilistic nature of fatigue, where there's a very complex material response that has many influential interacting factors, and equally a varying relationship between metallurgy, defects, and mechanics. There are also, of course, statistical reliability issues with data and its processing. And the presentation will end with some thoughts on how the fatigue community might progress exploitation of our advanced techniques to enhance understanding of the physics of crack growth. I think the fatigue research has two primary aims. Firstly, to predict life under cyclic loading of components or structures, and this can occur either during design or in service when you're involved in condition monitoring. And secondly, to develop a better understanding of the physics of crack initiation and growth, which will of course input into developing better life prediction. Those aims do not necessarily align, because simplified life prediction techniques are more useful, whereas the physics of crack initiation and growth is not so simple. It's a multi-scale problem, it's non-continuum, anisotropic, non-homogeneous, and overlaid with issues of probability and variability. And of course, all of those things are not really what industrialists want to take into account in a simplified life prediction technique. It seems to me that during the initial work on fatigue and fracture in the 1960s and 70s, two main thrusts can be distinguished. The first one was a more metallurgical approach to crack physics, and it includes things ranging from atomistic simulations of cracking to dislocation-based models of early crack growth initiation. The second approach is more of a mechanical engineering approach to the mechanics of fatigue crack growth, and that ranges from things like the experimental measurement of crack growth using, for example, crack tip gauges that you can see in the picture, to Paul Paris and his DADN delta K relationship. This really reflects that there were two sets of people working on fatigue and fracture in the early days: metallurgists, material scientists, and mechanical and civil engineering. In the metallurgical and crack physics viewpoint, there was a strong emphasis on microstructure. And one of the difficulties, of course, is that microstructure includes crystal structure, dislocations and other defects, as well as the results of processing and fabrication. And the sort of things you get out of a microstructure approach is, for example, the Navarro and de los Rios model for small fatigue crack growth. There's also, of course, an interest in transmission electron microscopy and scanning electron microscopy coupled with dislocation mechanics. And that led to major advances, e.g. striation formation and in the science of fractography. And there was an emphasis perhaps on influences of crack tip plasticity, for example wells at the Welding Institute and the crack tip opening displacement. Perhaps in contrast, in the mechanical engineering community, there was more of a mechanics of crack growth approach. So you get Irwin and the stress intensity factor, which is an elastic parameter that characterizes a plasticity-induced phenomenon, or a certainly nonlinear constitutive phenomenon. Paul Paris and the relationship between crack growth rate and the range of stress intensity factor, and influences of the crack tip plasticity, for example, Wolff-Elber, and the concept of fatigue crack closure. You also got the concept of similitude. And the idea here is, as you know, that two cracks of different sizes will have equal values of stress intensity range if they have equal plastic zone sizes with equal stress and strain distributions ahead of the plastic zone, and the growth rate will then be the same in the two cases. However, that assumption is invalid when either microstructural damage mechanisms or crack tip shielding are not the same in both cases. In the mechanical engineering community, there's also a strong drive towards standardization of toughness and fatigue testing and of data analysis, because it was necessary to ensure compatibility of results from different laboratories. The limitations inherent in characterizing plasticity or a damage zone-induced cracking phenomenon via the numerator of an elastic crack tip stress term, i.e. stress intensity factor, have never been fully resolved. And the focus on crack closure as simply a mechanical issue of crack weight contact, in my view, has also hindered understanding of the other mechanical and microstructural influences on crack growth mechanisms, and hence has limited our understanding of crack physics. These unresolved issues have led to an increased focus on other parameters to characterize fracture, such as the absorbed energy and the energy that might be absorbed and dissipated during crack growth, which of course harks back to the Griffith strain energy release rate. However, energy approaches still largely ignore the metallurgical influences on crack growth and often rely on experimental fitting parameters. You've also had multi-parameter approaches to characterizing the crack tip field in recent years, but it seems to me that some 50 plus years after Paris, Laird and Elber, it's appropriate in the context of our understanding of crack physics to pose the question, quo vadis, where are we going? One of the issues in our lack of understanding, in my view, is that cracking requires an energetically favourable situation and a critical stress relative to the local microstructural condition. And linear elastic fracture mechanics is a macroscale elastic approximation to the localized, non-linear phenomenon of crack tip deformation. So it's not going to work that well, under certain conditions at least. The J integral is in its turn a nonlinear elastic energy parameter, but does not capture the effects of unloading. And these effects may include changes in residual stresses and strains, changes in the constitutive response of the material, and changes in local microstructure. Strain energy approaches are more promising, but they're still largely based on solid mechanics, and it's difficult to consider crack physics in a metallurgically sound way. In terms of the similitude limitations on our understanding, if shielding of the crack tip changes, then the effective driving force is also different, and you then require an appropriate response scaling law to maintain similitude. And delta K effective was an attempt at one such scaling law, and it was defined following the realization that crack surface contact could occur even under tension loading. Crack surface contact had been expected to occur in loading cases when the stress ratio was less than 0, and negative values of K are therefore assumed not to influence crack growth rates. Hence, only the tensile part of the complete load range is used to assess the range of stress intensity factor. However, depending on how you define stress intensity factors, negative stress intensities can have an influence on crack growth, as for example in the model I've developed myself with Colin Christopher and Ian Patterson, the CJP model. Crack closure has proven to be particularly interesting to the fatigue community, and a major research effort after 1970 has been focused on understanding it. And this is focused on things like the magnitudes of closure in plane stress and plane strain. Does closure in plane strain exist? The hysteresis in load cycling between K opening and K closing, which are generally not identical. And again, why does that occur and which value is more representative of, crack contact? The mechanisms involved in crack closure, what are the optimal techniques and specimen positions for measurement, and correlating crack growth rates at various stress ratios in different environments and for different crack sizes. And that work has thrown up a number of controversies and problems that have never really been fully resolved, and I give you one reference to a paper here. A major problem with crack closure in terms of crack surface contact is that it doesn't adequately capture all the influences that are covered by crack tip shielding, for example the paper by Ritchie. And again, in another paper by Ritchie, shielding was well summarized, and he considered crack growth as a mutual competition between intrinsic microstructural damage mechanisms that promote crack extension ahead of the crack tip, and extrinsic crack tip shielding mechanisms which primarily act behind the crack tip to retard crack growth. And in his view, this approach provides commonality between the fatigue of ductile and brittle materials, which differ only in the importance of these intrinsic and extrinsic mechanisms. The images on this paper are from Ritchie's paper and basically show extrinsic toughening mechanisms, and these include crack deflection and meandering, zone shielding and contact shielding, and combined zone and contact shielding. And he has an illustration that differentiates between his extrinsic toughening and intrinsic toughening. However, extrinsic shielding can arise, in my view, from either zone shielding or contact shielding, with zone shielding including metallurgical aspects. One of the defects of the Ritchie model is that it does not include any potential influences of compatibility at strain at the elastic plastic boundary, and in fact this seems to be largely ignored by most workers in the field. It is clear, however, that as Poisson's ratio is 0.5 in the plastic region and of the order of 0.3 in the elastic region, a compatibility stress and strain has to be induced at the elastic plastic boundary, and it seems that this stress and strain is likely to affect the crack tip field and to be crack length dependent. And support for this concept can be found in several of the very limited number of dislocation models of closure, and the one I shall focus on in a moment is the one by Riemelmoser and Pipin. Whilst Riemelmoser and Pipin did not explicitly talk about compatibility at all, they presented a dislocation mechanics model for plasticity-induced closure in plane strain and showed that dislocations in the crack wake elastically rotate material in the wake, and that causes material transport to the crack tip. And so this is an illustration here. And of course, in principle, at the elastic plastic boundary, you should therefore get a stress-strain field caused by compatibility. Their model considers elastically constrained plastic deformation, and that therefore implicitly considers compatibility. And they show in their model that the transported wedge of material has a very strong effect on crack shielding. So you can see on the left this little wedge, and on the right the shielding capacity is a function of its length in units of the plastic zone size. So it seems to me, and indeed to others, that it's clear that there are a number of measurement and interpretation difficulties with K opening, K closing, and hence with the definition of any delta K effective. It's also clear that the applied load below the crack opening point may contribute to crack growth, both in aluminium and copper alloys, and I cite two references there, one some work I did years ago and another by Chen, Weiss and Stickler. And that phenomenon was termed by the latter authors as strain intensification. And so delta K effective often provides an inadequate characterization of effective driving force, and that's particularly noticeable in work on overloads and underloads. And it's becoming clear from several workers that you may need to consider the combined influence of ratcheting, perhaps of Kmax, and of any delta K effective. And of course you still need to know how to define delta K effective, which is not clear. So as I already mentioned, over the years these uncertainties have led to the proposal that multi-parameter models are maybe required to characterize the effective driving force on cracks and hence the growth rates. And these multi-parameter models include possibly additional terms in the Williams or Westergaard stress field equations, and I give you some references. The T-stress, which is known to be an important influence on crack tip plasticity and in fracture mechanics, and perhaps on combinations of delta K and K max, particularly at high ratios, stress ratios. And I give you there a reference by me, but I must say that my memory, Suresh and Richie proposed this first, but I can't find the original reference for that. In my own work, after many years of studying fatigue crack closure in the light of what Riemel Moser and Pippan and Sadananda and Vasudevan had said in their work, I ended up proposing the CJP model with colleagues Colin Christopher and Ian Patterson. And that is a full field modified plane stress elastic approach to the forces on which stress intensity characterization of the crack tip field is based. And what I hope it does a little bit better is consider the influences of the total plastic enclave on the elastic field that drives crack growth. What it does, that's somewhat controversial perhaps, is leads to new formulations for stress intensity factors that are associated with the crack tip fields. And these have two main components, a component that drives crack growth and a component that retards crack growth. A net crack growth, or the effective delta K, represents the sum of those two components. In this case, you have to be careful because negative Ks can actually retard growth and positive Ks will accelerate it. And it depends on the way that these stress intensity factors are defined relative to the crack growth direction. What seems to be clear after a considerable amount of work with colleagues in Haiyan and in China is that the model gives a more accurate driving force over a wider range of crack growth rates than the Paris relationship. And while I'm on the topic of the Paris relationship, I would like to say that the Paris relationship is not a law. It is not based on any physical understanding, and physical understanding is the basis of the law. To illustrate the CJP's model's success in characterizing crack growth rates compared with Irwin and Paris, I present data here for grade 2 titanium, which regrettably doesn't have much of a mean stress effect, so there's very little stress ratio change in the crack growth rates. However, you can see that the data on the right, which is characterized using delta K CJP, is really well rationalized and correlates onto pretty much a single line, as against the data on the left, which uses delta K. Work has also demonstrated that the CJP model, which by the way stands for Christopher, James and Patterson, gives a more accurate characterization of the size and shape of the crack tip plastic zone than either Williams or Westergaard. So it seems that its original intention to be a more accurate elastic stress model of crack tip fields is possibly correct. And so the data below is for the von Mises yield criterion, a stress ratio of 0.6 in grade 2 titanium CT specimens. And the various colors indicate the CJP model, the Westergaard model, and the Williams model. I would now like to consider issues around numerical analysis and experimental capability. So it's clear that computing processor power has increased very dramatically since 1980, but it's also clear that many finite element models of crack closure have largely remained the same. There's a generally inappropriate characterization of crack growth by node release at a chosen point in a load cycle, and that's not clear how that takes account of the real metallurgy of crack physics. Very small crack increments are often modeled to save computer resources. There's a limited amount of work around that shows that this is in itself not terribly accurate. It's not clear how the Poisson's ratio effect compatibility would be included in FE models. It's checked against often inaccurate experimental data, and as was first noted by Anders Blom in the early 1980s, it's odd that numerical results for first node contact, which is usually about 10-20 microns, are similar to the values measured for closure using compliance and crack mouth clip gauges or backface strain gauges, which are positioned many millimeters from the crack tip. Equally, the models are often 2D and not 3D, and in my view it would be very helpful to have a round-robin approach to FE modeling to determine the relative influence of all these effects on the results. Moving on to experimental capability and considering digital image correlation. This is a very powerful technique where you can obtain accurate 2D or 3D surface stress or displacement fields. It works across a range of scales from specimens to structures through changing the objective lens used on the system. It's easily portable for deployment in industry, and it's largely replaced the more complex photoelasticity in full field experimental measurements. DIC is very useful in quantifying plasticity-induced shielding, and displacement fields can be solved for either stress or strain using an analytical model for the crack tip fields. And equally, the commercial software will solve directly for stress intensity factor, but then you are getting the inaccurate Irwin stress intensity factor. And it's my thesis here that one of the things that's holding us back in experimental capability with DIC is that the standard SIF solution stress intensity factor do not increase our understanding of the physical mechanisms that underlie important shielding-induced crack growth rate phenomena. DIC results are very sensitive to crack tip location, to the speckle pattern and how well it's put on, as well as to facet size and overlap. But nonetheless, you can do some work to determine optimum positions for all these things, and you can end up getting very respectable data. However, when you go to compare data from two different people in two different laboratories, it's never clear that they're directly comparable. And I have had some problems with students in my laboratory trying to duplicate what is done in Cayenne. DIC is also very useful for measuring crack tip opening displacement, although it's perhaps complex to resolve the very small scale displacements in crack tip opening. But crack tip opening displacement is a very useful parameter. It's been widely applied to characterizing fatigue crack growth rate and gives you an effective fatigue crack growth rate, but it doesn't tell you very much about crack physics. So as I note here, it's an experimental challenge for DIC as displacements are small. There's only been a limited number of studies, but you can successfully measure the plastic component, and colleagues at Cayenne have done that in aluminium alloys. And the range of CTOD, the plastic range of CTOD, provides a linear fit to DADN at high and low stress ratios. So as I've said, it adequately seems to characterize effective driving force, but it does not give insight into the shielding mechanisms. And you can only extrapolate at constant amplitude loading under similar test conditions. There would be, I think, predictive difficulties with variable amplitude or spectrum loading. But one very interesting thing is that, according to work by Vasco-Olmo and Díaz in Cayenne, the technique unambiguously gives the good position, correct position, to measure an accurate CTOD value. So this slide just illustrates typical CTOD data you can get using digital image correlation, and this is for a crack 9.4 millimeters long in 6082 T6 alloy. And it shows you the loading and unloading, how you define the delta crack tip opening displacement plastic, and then shows the linear correlation you get between stress ratios of 0.1 and 0.6. In terms of using digital image correlation to support the development of new analytical models for crack tip fields, the CJP model was validated using phase stepping photoelasticity and digital image correlation. The advantages of the CJP model appear to be that it potentially offers new insights into mechanisms involved in stress ratio and overload effects from the way the equations are defined, and we'll consider that in a moment. But you can also solve for stress intensity values directly from the displacement field. Another issue is that the stress intensity factor in the CJP model is defined in terms of the crack tip and appears to be geometry independent. That's useful. You no longer need a compliance function between various specimens to get the stress intensity factor. And you can rationalize crack growth rate data over a wider range than you can using Irwin or Paris, as I've already said. Its disadvantages, and of course everything has disadvantages, is it's tricky to interpret mathematically in terms of mechanistic contributions from the individual force terms used to define the model. And it is analytically and experimentally complex, without appropriate MATLAB routines to make it all somewhat easier. Independent evidence that the CJP model appears to correctly predict the effective driving force comes from work done by Noel at Oxford, and his team used a different DIC method to measure delta K effective in the crack wake, and they compared their measurements with the predictions of the CJP model. And you can see here you've got Noel measurements in red and the CJP model in black, and they're very close. The CJP model appears to have a bit of a perturbation near the top end of the load cycle. Whether that's accurate or not, I'm unclear at the moment, but it is far more accurate than certainly Irwin. This slide illustrates how the CJP stress field equation will give you some insights into the underlying physical mechanisms, but it is mathematically complex to identify which parts of the forces give you which influences. So the equation that defines the CJP stress field is given here, and you can see it's got a number of parameters in it which you solve for: B, E, C, F, etc. And the two stress intensity factors that we define in this, which is Kf, a forward factor driving it, and Kr, a residual or retarding stress intensity that retards crack growth, use these parameters in them. And so in principle, if they change, if the values of A, B, E, etc. change during, for example, overload cycles, it should be feasible to get some information as to which parts of the stress field are causing that. So this overhead shows you the changes in A, B, and E, or in fact in this case just A, but we'll come on to the others, change after overload cycles. First of all, 100% overload and 125% overload. So these graphs show you the changes in the parameter A before and after 100% overload and 125% overload in specimens of the same 2024 T3 alloy. And the difficulty comes in interpreting that data in terms of the active mechanisms during an overload cycle, but it can be done. Moving on in terms of considering experimental capabilities of thermoelastic stress analysis, it's a widely used non-contact infrared technique, and it gives you delta K effective values on dynamically loaded specimens from full field surface stress maps. You measure millikelvin temperature changes as associated with cyclic loading, and you need a high loading frequency to achieve adiabatic conditions. And new infrared array detectors enhance its full field capability. It's supposed to be sensitive to closure effects, as measured by compliance, and can measure the cyclic plastic zone size, because there is a characteristic change in phase that occurs near the crack tip, which is assumed to indicate a breakdown in adiabatic conditions due to crack tip plasticity.
Thermoelastic stress analysis is a full-field experimental technique that provides temperature variations at the surface of a cyclically loaded component. Under elastic conditions, this temperature variation is directly related with the change in the sum of principal stresses. This slide shows an illustration shot of data obtained using a TSA commercial system, as well as a summary of the methodology employed to obtain delta K from the analysis of the measured stress field. This technique has the advantage that it can be used on one side of the specimen together with DIC simultaneously on the other side of the sample. This seems to have a significant potential for unlocking the crack physics, since as previously mentioned, there are still some issues with TSA that need to be studied in a deeper way. This slide shows a typical set of images obtained with TSA in terms of polar coordinates and Cartesian coordinates. The temperature variation associated with the thermoelastic effect happens at the same frequency as the loading signal. Thus, to start the thermal emission due to the thermoelastic effect, the loading signal is employed as a reference signal in a locking process. However, to achieve adiabatic condition to avoid heat conduction over the specimen surface, the loading frequency needs to be high enough. As a result, the thermoelastic information is presented as a vector where the modulus represents the amplitude of the temperature variation due to the thermoelastic effect, and the phase represents the phase difference between the reference signal and the thermal signal. Under adiabatic condition, this phase difference remains constant. However, at the crack tip, there exists an irreversible heat generation due to plastic work, which led to a loss of adiabatic conditions. This loss of adiabatic condition can be easily identified as a phase shift and the crack tip area.
As I've mentioned, there is some work by Rory Spencer in his PhD thesis at the University of Liverpool that sheds a little bit of doubt on whether thermoelastic stress analysis does actually measure crack closure and the effective plastic zone size. So he used TSA and 0.8mm thick CT specimens in a 304 stainless steel, and his work demonstrated that a purely elastic stress distribution generated a phase image similar to those that have been linked with plasticity, and therefore those results cast doubt on using the phase method for investigating cyclic plasticity. He therefore used a second harmonic method with post-processing to identify a plastic zone. But it's interesting the data deviated markedly from Irwin's plastic zone correction and from the phase method, and a frequency dependence was observed in his results over the range of 10 to 80 Hz. So the case for using TSA in plasticity studies is not yet proven. So summarizing this very brief overview of several full field techniques, there are now some very advanced techniques available to measure crack tip fields, but they all potentially have unresolved issues. With TSA, it's not clear exactly what's indicated by the phase or second harmonic methods, and validation against simple plasticity models, e.g. Irwin or Dugdale, is not likely to be conclusive. Equally, TSA does not give insight into crack physics and the underlying crack growth mechanisms. DIC can give values for the range of crack tip opening displacement, the plastic range, and hence delta K effective may provide an effective driving force if you define delta K effective accurately, but it does not give insight into crack physics without linking to an analytical model, an advanced analytical model of crack tip fields. So after 50 years, in my view, shielding remains largely unresolved as a very important fatigue phenomenon. One of the useful things about these full field techniques that I've mentioned is that combinations of techniques used on the same specimen have significant potential to unlock understanding. You could use them on opposite sides of the same specimen, and you should, in principle, get increased understanding of what their output data is actually showing you, and hence enhanced understanding of crack plasticity and physics. So an example might be TSA with DIC and the CJP model may resolve what TSA is actually measuring in the phase or second harmonic methods. Another issue that is important going forwards, I believe, is standardization of test techniques, of specimens where possible, and of data analysis. That would improve comparability of results from different laboratories, and that would be really quite useful. I believe that it is very useful going forwards to further explore the utility in describing crack tip fields of formulations other than the Williams or Westergaard, which seems to be used almost exclusively when people do work on crack tip fields and crack closure. The CJP model is one such attempt. It includes more of the influences that are believed to result from crack-induced plasticity, and so far we have Mode 1 and Mode 2 solutions for crack tip stress and strain fields directly from displacement data, but its disadvantage is that it's complex to use. We are trying to work on online interfaces that would allow easy analysis of the data and would make it more widely available. The model by Pommier and Hamin is another one. They noted that crack tip plasticity causes additional displacements that is not captured by Westergaard. And to get a value for that additional plasticity, they compared an elastic plastic FE model with the elastic crack solution, with the difference between the two giving plastic contribution. And some work by Knoll has examined the model of Pommier and Hamin and the CJP model and concluded that they both are dealing with the same issues, although in different ways. But there is significant scope for further work on both those two models, their differences, and indeed on other models. So, moving on to some concluding remarks. In the early days of fatigue and fracture research, there were two main thrusts developed, based either on metallurgical or mechanical engineering approaches. These approaches have some limitations. There were attempts to overcome these by focusing attention on two main concepts: delta K effective and crack closure. In my view, however, closure does not adequately capture all the crack shielding influences. So that leads to a fundamental question regarding the relative roles of crack closure in terms of crack weight contact and crack tip shielding, which is much broader and more likely to be based on crack physics and crack mechanisms. A variety of different physical models have therefore been developed to characterize effective driving force. The CJP model is one such model, which considers the influences of the plastic enclave on the elastic field in what we believe is a more holistic way. The model by Pommier and Hamin is another model. The presumed ability of the CJP model to more successfully characterize crack tip stress fields and hence crack tip shielding have been demonstrated through experimental techniques like the characterization of the size and shape of the plastic zone. So it seems to provide a more accurate, elastically derived crack driving force than the Paris relationship. Considering numerical FE models, the way they model cracks has largely remained the same over the last 40 years, despite the fact our processing power has increased very dramatically in that time. Optical techniques such as DIC or TSA in combination with accurate mathematical models seems to be a promising option to better understand the physics of fatigue. And standardization of test techniques, specimens and data analysis would contribute greatly to making further advances. Currently the data is extremely scattered, and when you try and repeat experiments yourself, they don't always give the same answers as reported in the literature. The authors acknowledge financial support for the work done at Jaén from the Spanish Ministerio de Economía and Competitiveness. We also acknowledge the significant input made by Colin Christopher, Ian Patterson, postdoctoral research assistants and PhD students over the last 20 years in the development of the CJP model and in the development of the underlying thinking. Finally, I thank you all for your attention to this presentation and apologize for the fact that I'm not very good at talking to computer screens. This presentation may have been more dynamic and interesting if I'd been able to talk to you as an audience personally. Thank you.